So today in this class we are going to start up with NCERT class 12 physics chapter 2 electric potential and capacitance this is what we are going to start. Okay, electric potential and capacitance. Today we'll focus on electric potential. So potential, when I say potential, in class 11 also you have studied so much about this gravitational potential, okay, in class 11 chapter 8. Actually the word potential is not properly defined in capacitance, or in physics the word potential is not properly defined. We cannot define exactly what is potential in physics, but we can define what is electric potential difference. That we can define very easily. Electric potential difference. This is what we can define. The word potential is not properly defined in physics when I say only potential. But when I say electric potential difference, that we can easily define. Okay? You just make any 2 points. Okay, consider 2 points, A and B. Let's say that VA is the potential at A and VB is the potential at B. Okay? Yes. Now, you place a charge Q0 at B. What is Q0? Our experimental charge. Okay, since chapter 1, this Q0 has been very useful. Q0 is our experimental charge. We call it as test charge, and it's a vanishingly small positive test charge. That means this Q0 itself, it does not produce any electric field. Okay, does not produce any electric field by itself. Now, if you want to find out the electric potential difference between 2 points A and B, what you need to do? From this point B, you bring this test charge Q0 to the point A. Is it okay? So, in order to bring this test charge Q0 from B to A, some work has to be done. And who does the work? Who does the work? Work has to be done by the external agency. Okay? The work has to be done by the external agent. Suppose you do the work. You go and carry this test charge from point B to point A. So you have done the work, you are an external agent. Is it okay? Yes. Now, as you bring this test charge Q0 from B to A, the steps that you take in going from B to A should be infinitesimally small steps, so that there should be no change in speed of Q0. Okay, the speed of Q0 should not be changed. Also, the kinetic energy of Q0 should not be changed. The speed should remain constant as you bring Q0 from B to A, or the kinetic energy of Q0 should remain constant as you bring this Q0 from B to A. Is it okay? So you can bring this test charge Q0 from B to A either in this direction, following this path, either you follow this path, or you follow this path. Is it okay? And that work has to be done against the electrostatic force. Alright? Yeah. So how much work is done by the external agent in bringing this test charge from B to A is known as electric potential difference between 2 points B and A. Are you getting that? Huh? Are you following? Yes. So in order to define what is electric potential difference, I will repeat again. You consider 2 points A and B. Let VA be the potential at A, VB be the potential at B. Is it okay? If you take this B to a infinite distance, then we cannot determine its potential, alright? So make sure that they are at finite distance, alright? Now, in order to find the electric potential difference, what you need to do, you place the test charge Q0 at B, and you bring this test charge Q0 from B to A. Is it okay? So in order to carry this test charge, in order to bring this test charge Q0 from B to A, some work has to be done. And who is going to do that work? By an external agent. But as you bring this test charge Q0 from B to A, it has to be done so slowly. Okay? It has to be done so slowly that there should be no change in speed of Q0, or there should be no change in kinetic energy of Q0. That means the steps that you take, each step that you take in bringing Q0 from B to A should be like infinitesimally small steps. If we bring Q0, okay, taking infinitesimally small steps, alright, then there can be no change in speed, or there can be no change in kinetic energy. So, in order to bring this Q0 from B to A, some work has to be done by the external agent. So how much work has been done by the external agent in bringing this Q0 from B to A is known as the electric potential difference between 2 points A and B. Okay? So electric potential difference is defined as you are bringing it from B to A. So electric potential difference is defined as VA minus VB. Potential difference means difference in the potential in A and B. VA minus VB is defined as work done by the external agent. Work done by the external agent in bringing this test charge from B to A. Is it okay? So potential difference between any 2 points is defined as work done by the external agent in bringing this test charge upon Q0. That means work done by the external agent per unit test charge. Here you are bringing the test charge from B to A. So potential difference between any 2 points A and B is defined as the work done by the external agent from B to A per unit test charge. Work done by the external agent in bringing it from B to A per unit test charge, that is known as your electric potential difference between 2 points. Alright? Yes. But if you are asked to define electric potential at a point, then how are you going to define that? In order to define electric potential at a point, then what you have to do is you have to bring that test charge from infinity to that particular point. Now, in order to define electric potential at a point, what you have to do, you have to bring the test charge from where? From infinity to that particular point. Alright? So you want to define what is the electric potential at A, right? Okay? What is the electric potential at A you want to define? That means you have to bring the test charge from infinity to that particular point. Alright? Let VA be the potential at A. Then the potential at infinity will be V infinity. So in this case, we have to assume assume, just theoretical assumption. Actually, we cannot say what is the potential at infinity. We cannot say. But we have to assume, in order to define the electric potential at this particular point, we have to assume that the potential at infinity is zero. Assumption. Okay, we cannot say, actually we cannot say what is the potential at infinity, but we need to assume that it is equal to zero. No? So, electric potential at a point is defined as work done by the external agent, in bringing this test charge from infinity to that particular point A, right? It means electric potential at a point is defined as work done by the external agency in bringing from infinity to A per unit test charge. That is how we define electric potential at a point. Work done by the external agent in bringing the test charge from infinity to that particular point. And this work has to be done, against the electrostatic force. Is it okay? This work has to be done against the electrostatic force. So this work done by the external agent is done against the electrostatic force. Against the electrostatic force. Electric force, we say in short, electrostatic force. Second thing, very important point to remember, the second point, there are 3 points that you need to note. Here, the work done by the external agent is always against the electrostatic force. Second one, it should be the work done should be path independent. Path independent. In class 11, work, energy and power, you might have studied that, okay? Work done is path independent. Suppose you do the work done in bringing this Q0 following this path. You can do it following this path, or you can do it following this path. No matter which path you follow, work done will always remains the same. And work done is path independent only if the force is conservative. Only if the force is conservative. In class 11, you have studied about conservative and non-conservative forces. Is it okay? So only if the force is conservative, then it is path independent. And you are doing the work against this electrostatic force. You are doing the work against the electrostatic force, and the work done is path independent. That means the force must be conservative. That means electrostatic force is conservative. That is why the work done by the external agent is path independent. So the work done is path independent. Why? Because since electric force, electrostatic force is conservative. If you are not clear with this, okay, about the conservative, non-conservative forces and about the work done, you can just go back and home and check with the class 11 physics ones. Then things will become clear. Everything is just given in very simple in your ABC, okay? And number 3, there is again one more condition, and I have told you that this Q0 should not produce any electric field by itself. Okay, this Q0 should not produce any electric force. Electric force by itself. So these are the 3 points that you need to remember. These 3 conditions that we have to follow. Is it alright? Any problem? Is it okay? Yes. Okay then. So electric potential at a point is defined as the work done per unit test charge, okay, in bringing it from infinity to that particular point against the electrostatic force. 3 points that you need to know. First one, the work that you have done is always against the electrostatic force, means should be done against the electrostatic force. Number 2, work done is path independent, and work done can be path independent only if the force is conservative and you are doing against the electrostatic force. Okay, that means the electrostatic force is conservative force. The third one, the test charge Q naught should not produce any electric field by itself. Those are the 3 things that you need to remember. All right. Okay. So the next one is, let's find out the expression for the electric potential at a point. Okay, since we have defined it, let's express it. Suppose like if it is too much for you, I can just pause so that you can write those things now. Again, we will continue. Expression for electric potential at a point. Expression for electric potential at a point. Okay. So let's consider that a charge Q, a positive charge Q, is placed at the point A. Is it okay? And I want to find out the electric potential at this point P, which is placed at a distance r from A, due to this charge. I want to find out the electric potential at this point P due to this charge which is placed at A. Is it clear? No? Q means it's plus Q, okay? I'm considering a positive charge here. Any expression that we want, we always consider a positive charge. That makes things easier. So in order to find out the electric potential at this point, what you have to do, if you want to find out the electric potential at any point, what do you have to do? You have to bring the test charge from infinity to that particular point, right? Is it okay? Yes. So suppose this is your infinity. Let's say that this is your infinity. Q naught is at infinity. So we have to bring the test charge from infinity to this particular point. But we do not know what is the potential at infinity. If you consider some distance from infinity, suppose Q is a point from some distance from infinity, at some distance from infinity. Also then we do not know what is the potential at this point. Kobo na paribo. Infinity lang kobo na paribo. Our infinity for all of ahilipi, ito laka point p. We do not know. We cannot say what is the potential at this point. Is it okay? So what I'm going to do is, in order to bring the charge from infinity to P, instead of bringing the charge from infinity to P, I will take it from P to infinity. Because, why? Why, can you like just guess, like, instead of bringing from infinity, I cannot bring it from infinity, no. Why? Because we do not know what is the potential at infinity. So instead of bringing from infinity, I'm going to bring it from point P. See, taking it from point P will be very simple. Let's take it from P to infinity. Let's take this Q naught from P to infinity. Already there will be an electrostatic force due to this charge. Now, this Q naught, okay, there will be an electrostatic force on this Q naught due to this charge. Okay, so that electric force will just take this Q naught by itself to infinity. Right? Now, there is one problem. As you let this electric force to do the work, as you go, we know that electric force according to Coulomb's law is given by 1 by 4 pi epsilon naught into product of the charges upon r square, square of the distance. That means F is proportional to 1 by r square. So as you go away from the charge, as you go away from this point A, from this charge Q, then the force will decrease. Is it okay? That means F becomes a variable force. F becomes a variable force. As you go away, force will decrease. Is it okay? Yes. So if F becomes variable, then what will happen? The speed of Q naught will change, and the kinetic energy of Q naught will also change. Is it okay? Yes. But that can be settled. That can be done with. We can settle the things. But in order to bring from infinity to P, we do not know what is the potential at infinity. Is it okay? So things becomes difficult. So we will do this in the other way. Is it okay? Now, and we know that electrostatic force is conservative. Electrostatic force to conservative. Since the electrostatic force is conservative, you see, work done by a conservative force in a closed path. Work done by a conservative force in a closed path is always 0. Is it okay? Yes. What I mean to say is, suppose you take the charge from B to A. You take this Q naught from B to A, and you take it from A to B again. Then the work done in bringing from B to A and then A to B, B to A and then A to B will be 0. That means work done in bringing the test charge from B to A plus work done in taking the test charge from A to B again, will be equal to 0. In that case, WBA will be equal to negative of WA. Are you understanding what I'm trying to say here? That means work done by a conservative force in a closed path is 0. You take this test charge Q naught from B to A and then from A to B. Then the total work done will be 0. Total work done means work done in bringing from B to A plus work done in taking again from A to B, right? In that case, WBA, work done in bringing from B to A, will be negative of work done in taking it from A to B again. That means, instead of bringing it from infinity to A, I'm going to take it from P to infinity. So that work done in taking the charge from P to infinity will be negative of the work done in bringing from infinity to P. So if I find this one, then I get this one. Hence our definition is done. Work done in bringing the body from infinity to point P. Are you feeling that? I feel correct, na? Yes. I cannot bring it from infinity. No, because I do not know what is the potential here. So what did I do? Instead of taking it from infinity, I'm bringing from now P. I'm taking it from P. Now P infinity pra anabrado P pra hiluijas. We know that work done by a conservative force in a closed path is 0. So the work done in taking the test charge from P to infinity will be negative of the work done in taking from infinity to A. So if I find this work done in taking from infinity to, or from P to infinity, then I can obtain the work done from infinity to P using this work done by a conservative force. Are you getting that? Yes. See, your knowledge must be a little bit clear about work, energy and power. Snub and me, we have studied last year about this. Okay, work done by conservative, non-conservative forces. I don't know, Hilo, how much you have studied. I cannot say about that. Okay, but you're understanding now, no? Okay. Work done by a conservative force in a closed path is 0. That means work done in bringing the charge from A to B and then taking it to A again will be 0. This can be divided as work done in taking from A to B plus work done in taking from B to A will be 0. In that case, work done in taking from A to B will be equal to negative of work done in bringing from B to A. To infinity anibo na parity pra hi loi jaw aru negative pra multiply kori dibo hoise. Now, this is the concept here, okay? This is the only concept here. The rest of the things are very simple. So, consider that the charge plus Q is placed at the point A, and I want to find out the electric potential at this particular point P due to this charge. Now, P is placed at a distance R from A. Now, since I cannot bring the test charge from infinity to P, so I'm going to take it from P to infinity. Is it okay? Yes. So what is the electrostatic force at the point P? Since I have placed Q naught at P, Q naught will experience an electrostatic force, right? So according to Coulomb's law, the electrostatic force will be given by 1 by 4 pi epsilon naught. Let me write only the magnitude. 4 pi epsilon into Q naught upon R squared. Is it okay? So this charge Q naught will be brought to infinity from P by this force, by this electric force, okay? So electric force will act in this direction. So this is your electric force. See, you need not do any work, okay, here. Actually, when we think about this, keep Q naught here. Since there is electric force will take it. But here the problem is electric force is variable force here. Why? Because F is proportional to the square of the distance. So as the point Q naught goes towards infinity, the force will decrease. So the electric force becomes variable. If the electric force becomes variable, kinetic energy of Q naught will change, or speed of Q naught will change. But our ambition, our objective is to always keep the speed of Q naught constant, or the kinetic energy of Q naught should be constant, right? Now, to do constant force para lui jabuli nimiti, in order to take this Q naught from P to infinity with a constant force, what do you need to do? What do you need to do? How are you going to? This is variable force. So you, okay? So the speed of Q naught will not be constant, right? So in order to keep the speed of Q naught constant, Q naught laga speed constant rakhi bole nimiri. Stay brand new constant rakhi gena na. What do you need to do? What do you have to do? You have to apply another equal and opposite force to this. Now, check Q naught. If you keep this Q naught, electric force will just take it away. Now, without keeping the speed constant, without keeping the kinetic energy of Q naught constant. So, in order to maintain the constant speed or the kinetic energy, constant kinetic energy, you have to apply some force, equal and opposite force to this. Okay, you have to apply equal and opposite force. So some external force has to be applied, which is equal and opposite to this electric force. So some external force has to be applied. Okay, some external force has to be applied against this electric force in the equal and opposite to this electric force, so that this Q naught will be in equilibrium. It will be in equilibrium. If you apply equal and opposite force, Q naught be in equilibrium. In that case, now you can bring this Q naught without changing the speed to infinity, without change in kinetic energy to P. Are you getting me? Now see, this is a variable force. As you take it towards infinity, this will decrease. Accordingly, you have to apply this force. That means if this electric force is variable, external force applied will also be variable. So this one is a variable force now. Okay? So you are doing the work against this variable force. Is it okay? Against this variable force. Then what is the work done by the variable force? If the force is constant, here F is not, here this one is not constant. As Q naught goes away slowly from B, this electric force will decrease. Then you cannot keep this as constant, right? Is it okay? Yes. You also need to decrease the external force that you are applying in the opposite direction, okay? So this external force is variable. If this force was constant, then work done by a constant force is given by force into displacement. Force is given by, or work done is given by force into displacement. In class 9 and when you always study, oh, work done means force into displacement. Now, you always study in this way. But this is applicable only in one thing, only in one condition, if the force is constant. But if the force is variable, then you cannot use this relation. Okay? In that case, what you are going to do? Now, electric force is in this direction, the external force applied is in this direction, so Q naught will be in equilibrium. Since Q naught is in equilibrium, then we can now, by taking infinitesimally small steps, we can bring this Q naught to infinity without any change in speed. That means without any producing any acceleration. Okay? Let's say that dr is the small, infinitely small displacement. Okay? You have to bring this Q naught to infinity. That means, okay, you have to take small steps, infinitesimally small steps. dr is one such small step. And achieving this is possible due to this external force, right? Is it okay? Yes. So work is done against this external force. Okay? And this external force is variable. Work done by the variable force in taking this Q naught from P to infinity is given by integration of that external force dot dr, where dr is the small steps taken. And you are taking this Q naught from infinity, or from P to infinity. So this is the formula for work done by a variable force. If it is constant force, then work done means force in the displacement, done, finish, end of the story. Okay? But here work is done by the variable force. This is the formula for work done by the variable force. Okay? Now, dot product, okay, you can write in vector, happy now. Dot product of two vectors A and B is defined as A magnitude of B with the cos of the angle between them. Okay? So what I'm going to do is I'm going to do the same. Work done in taking the body from P to infinity will be equal to, what is the distance of this point P from the charge? R to infinity now. No? Your external force, your external force is equal and opposite to your electric force, right? So your external force will be what? Minus, equal and opposite to that of the electrostatic force. So minus of electric force. Alright? Is it okay? Yes. So your external force will be minus of the electric force. So minus 1 by 4 pi epsilon naught into Q naught upon R square, right? Into the displacement. Okay, before I write these things, let me convert this dot product to a simple product now. Dot product of F and dr will be F external times dr with the cos of the angle between them. F and dr Electric force is acting here, external force is acting here. What is the angle between them? 180 degree, 180 degree. If both the forces act in the same direction, then angle will be 0. But if it is in opposite direction, angle is 180 degree. What is the value of cos 180 degree? If you can remember, all silver teacups, yeah, cos of 180 degree is -1. 180 degree is here, right? All silver teacups, 180 degrees here. That means cos is negative in the second or third quadrant. Is it alright? Yeah, in the second quadrant, cos is negative. So cos 180 degree is negative. So r to infinity, what is your external force? -1 by 4 pi epsilon naught into q naught upon r square dr, right? Cos 180 degrees -1, correct? Minus becomes plus. R to infinity, 1 upon 4 pi epsilon naught into q naught upon r square times dr, correct? Right? 1 by 4 pi epsilon is constant, we have a value. So 1 by 4 pi epsilon naught. Magnitude of q remains the same, constant. Test charge is always constant, its magnitude never changes. Here r is your variable, we are changing r, right? So I will integrate dr upon r square within the limits r to infinity. How good you are in integration now? It's very important. What is the integration of dr upon r square? Very simple. Integration of x to the power n dx is x to the power n plus 1 upon n plus 1. Can I make dr upon r square in this form? Yes. So the work done by the external force in taking the body from p to infinity is equal to 1 upon 4 pi epsilon naught into q naught and then what? Dr by r square means r to the power -2 dr. Okay. So 1 by 4 pi epsilon naught into q naught integration of r to the, this is of the form x to the power n dx. N plus 1 upon n plus 1, right? From r to infinity. This is a definite integral, no constant of integration. -2 plus 1 minus 1. Minus, I will keep it here. And then 1 by 4 pi epsilon naught into q. Oh yeah, minus. Plus First though, f external was negative. After that, cos 180 was negative. Somehow we balanced. Now again we are getting negative. We can. It's no problem. R to the power -2 plus 1 will be r to the power -1. R to the power -1 means 1 by r. You are taking it from r to infinity. Is it okay? Yes. Now, proceeding with the integration, Wp to infinity will be -1 by 4 pi epsilon naught into q naught, right? And then putting the upper limit 1 by infinity minus putting the lower limit 1 by r. Instead of r, you just put r, right? So what is 1 by infinity? 0. So we have -1 by 4 pi epsilon naught q naught into -1 by r. Minus becomes plus. So 1 by 4 pi epsilon naught into q naught upon r. Now work done by a conservative force. Work done by a conservative force in a closed path is always 0, right? That means work done in taking the body from p to infinity will be equal to minus of work done in taking the body from infinity to p. So in that case, in that case, therefore, work done in bringing the body from infinity to P will be negative of the work done in taking it from P to infinity. Work done by a conservative force in a closed path is 0 according to that definition. So it will be negative of this 1 by 4 pi epsilon naught into Q naught upon R, right? Now we are finding the electric potential at P, right? So electric potential at P is defined as work done per unit discharge in bringing the body from infinity to that particular point against the electrostatic force. Is it okay? Now here 1 by Q naught as it is into this one is minus 1 by 4 pi epsilon naught into Q naught upon R. This Q naught cancel. So that is minus 1 by 4 pi epsilon naught into Q upon R, which is the required relation for the electric potential at any point. Is it okay? So now let us find out the expression for electric potential at a point. Okay? Yes. Consider that a charge plus Q is placed here. Okay. Now I want to find out the electric potential at this point P due to this charge. All right? Yes. So let's say that this P is at a distance R from this charge. Okay? See, this charge is placed here at A, and I want to find out the electric potential at this point due to this charge. Okay? Now, according to definition, electric potential at a point is defined as work done in bringing the test charge from infinity to that particular point against the electrostatic force. Is it okay? No? You want to find out the electric potential at this point. So according to the definition, okay, electric potential at a point is defined as work done by the external agent in bringing this test charge from infinity to that particular point. Okay? But see, the thing is that we do not know what is the potential at infinity. In the previous case, according to the definition, we assume that the potential at infinity is 0. But we cannot say about that exactly. Okay, that was just an assumption. We do not know what is the electric potential at infinity. Okay, so instead of that, instead of taking it from infinity, I'm going to take it from P to infinity. Instead of bringing from infinity to P, I'm going to take it from P to infinity. Now see, I'm going to place the test charge at P now. Why? Because I'm going to take it from P to infinity, right? Now at P, there will be an electrostatic force acting on this Q naught due to this charge. That electrostatic force is given by, according to Coulomb's law, 1 by 4 pi epsilon naught into Q naught upon R square. Is it okay? Yes. So if you keep Q naught at P, this electrostatic force will take this Q naught up to the desired point. Is it okay? Yes. But, so electrostatic force is acting in this direction. This is your electric force. But here, electric force is not a constant force. Of course, it is conservative, okay? But it is not a constant force. Why? Because as Q naught moves away from P towards infinity, the electric force will decrease. Why? Because electric force is proportional to the square of the distance. It's inversely proportional to the square of the distance. So as you go away, as the Q naught is taken towards infinity, then electrostatic force will decrease. That means this becomes a variable force. And if this becomes a variable force, the speed of Q naught or the kinetic energy of Q naught will change. Okay, but work has to be done without changing the speed of Q naught or without changing the kinetic energy of Q naught. So what do you have to do in order to take this test charge Q naught from P to infinity without changing the speed or kinetic energy of Q naught? An equal opposite force has to be applied to Q naught. Is it okay? Yes. Only if you apply equal and opposite force to Q naught, okay, then Q naught will be in equilibrium. And if Q naught is in equilibrium, you can slowly, taking infinitesimally small steps, you can take it to infinity without any change in speed, means without producing any acceleration or without changing kinetic energy. Okay, and see, since this force, electric force, is conservative force, we know that work done by the conservative force in a closed path is zero. We are not able to bring it from infinity to P, so we are taking it from P to infinity. And according to the work done by a conservative force, we know that work done by a conservative force in a closed path is zero. Let me show you an example. This is your point A, this is point B. Suppose you take the body from A to B and then bring it from B to A. Then that forms a closed path. So work done by the conservative force in taking the body from A to B and then from B to A and then from B to A will be zero, right? Now total work done in taking the body from A to B and then B to A can also be expressed as work done in taking the body from A to B plus work done in taking the body from B to A. So that means work done in taking the body from A to B will be negative of the work done in taking the body from B to A. So since we are not able to bring it from infinity to P, we will find out the work done in taking this test charge from P to infinity. So that work done in taking the test charge from P to infinity will be equal to the negative of work done in bringing the charge from infinity to P. Okay, so using the concept of work done by a conservative force, we can find out the work done in taking the body from infinity to P by taking it from P to infinity. Is it okay? Yes. So we are going to use this concept. And in order to take this charge Q naught from P to infinity without producing any acceleration, an equal and opposite force equal to electrostatic force, and force equal and opposite to this electrostatic force has to be applied to Q naught, so that Q naught will be in equilibrium, and taking infinitesimally small steps without changing any speed, Q naught can be brought to infinity. Is it all right? Yes. Now, this electric force is a variable force. Variable force, why? Because as Q naught goes towards infinity, this force will decrease. So it's a variable force. So you have to apply another variable force equal and opposite to this electric force, right? So that if this electric force decreases, you will also decrease that force. Is it okay? Yes. So a force equal and opposite to this electric force has to be applied. Okay? So this one will be your F, let's say external force. Okay? That means the F external will be equal and opposite to your F electric, right? Now let me take the magnitude. If you take the magnitude, then F external will be equal to F electric. Got it? That was the mistake I did before. Okay? Yes. If you take in vector, then okay, the external force applied will be equal and opposite to that of the electric force. But if you only consider the magnitude, then magnitudes are equal. Is it okay? Yes, in magnitude they are equal, but in direction they are opposite. Alright. Now this is your electric force. This is your electric force, 1 by 4 pi epsilon naught into Q naught upon R square. Then what will be your external force? F external will be also equal to this, equal in magnitude. 1 by 4 pi epsilon naught into Q naught upon R square. If you take the direction, then you have to write negative. But if you take the magnitude, they are equal. Are you getting that? Yes. So, what I'm doing now, I'm going to find out the work done in taking this test charge Q naught from P to infinity. Is it okay? And I am able to do that with the help of this force, okay, which is against your electrostatic force. Is it okay? Yes. Your electrostatic force is acting along this way. I'm putting the external force in the other way. Is it okay? Yes. Now, since this electric force is variable, and I am applying equal and opposite force, external force, okay, that means that external force that I am applying is also variable. Is it okay? Because electrostatic force is variable, because as you go away from, okay, P towards infinity, the electrostatic force will decrease. At the same time, you have to decrease the external force, right? Because you are applying equal and opposite force. Is it okay? Only then, without producing any change, without producing any acceleration, or without any change in speed or change in kinetic energy of Q naught, the work can be performed. So, if it was a constant force, if work is done by a constant force, then the work done will be given by force into displacement. But this is not a constant force. Here your F external is a variable force. Is it okay? So work done by the variable force cannot be equal to force into displacement. Let's say that under the action of this external force, dr is the small displacement that has been made by Q naught. Is it okay? Now, see, electric force is acting here. You are going to bring the test charge from P to infinity without any acceleration, so you have to apply external force. Now, so due to the action of this external force, you are able to bring this Q naught to infinity, okay, without changing its speed. So this F external is a variable force. Let's say that dr is the small displacement made, okay, in taking the charge from Q naught to infinity, okay. Q naught, dr is the small displacement that has been made, okay. Then that work done by the external force will be given by integration of your external force dot dr. This is the formula for work done by a variable force, integration of F dot dr. Now we are taking the test charge from P to infinity. We are taking it from P to infinity. When your test charge is at P, distance from this source charge was R, right? And when you take it to infinity, the distance will also be infinity, right? Now you see, displacement is made along this direction, right? Displacement dr is made along this direction. The force that you are applying is in this direction. So the angle between the force that you are applying and the displacement made is 180 degrees. So in that case, integration R to infinity, this dot product we can convert to scalar product, F external dr with the cos of the angle between them, because dot product of two vectors A and B is given by magnitude of A, magnitude of B with the cos of the angle between them. Are you getting me? Now, you are applying the force in this direction, displacement is made in this direction, so the angle, they're opposite to each other. So the angle between them will be equal to 180. Displacement 이팔에, force 이팔에, 또 cos 또 angle 도 180거든. Now integration r to infinity. Your F external is equal in magnitude to that of electric force, which is 1 by 4 pi epsilon naught into q naught upon r square dr cos 180 is minus 1. Clear? Are you clear with that? Now, this is equal to, this minus comes out, 1 by 4 pi epsilon naught is constant. It's a constant, we have a fixed value. Q, source charge, is undisturbed, no change in magnitude, so it's constant. Your test charge always remains constant. Only your R is variable here, because you are changing the distance, right? There is a change in displacement. So only R is variable. So integration R to infinity dr upon R squared. Now this can be rewritten as minus 1 by 4 pi epsilon naught into q naught r to infinity. dr upon r squared can be written as r to the power minus 2, r to the power minus 2 dr. Now, your work done in taking the body from p to infinity will be equal to 1 by 4 pi epsilon naught into q naught. Okay, integration of x to the power n dx is x to the power n plus 1 upon n plus 1. So integration of r to the power n dr will be r to the power n plus 1 upon n plus 1. We are integrating from r to infinity. So this is 1 by 4 pi epsilon naught into q naught. Minus 2 plus 1 is negative, I can take it here. And then r to the power minus 1 from r to infinity. Minus 1 by 4 pi epsilon naught into q naught. R to the power minus 1 means 1 by r from r to infinity, right? Now that is equal to, now this is now equal to minus 1 by 4 pi epsilon naught into q naught. Now we substitute the upper limit, which is infinity, so 1 by infinity, minus we substitute the lower limit in place of r, you're writing r, so same, 1 by r. Since 1 by infinity is 0, so we have 1 minus 1 by 4 pi epsilon naught into q naught times minus 1 by r again. So the work done in taking the test charge from p to infinity is given by minus plus, so 1 upon 4 pi epsilon naught into q naught upon r. Oh, this negative, I have missed out this negative. I have missed out this negative, right? And this negative, I have missed out. I have missed out this negative, see? Now, this negative has been missed out. The cos 180 was negative. Now, so I missed out that negative. Cos 180 is negative. That negative here, okay? And then this minus here, and again one more negative here will become plus. Is it okay? Yes. Oh yeah, why I'm doing chaos here? It negative. It cos 180 is negative. So this negative comes. This negative will become positive, right? No? Yes, it's yes. Yes. Is it okay? So 1 by infinity is 0, so we will have only minus 1 by r. So work done in taking the body from p to infinity will be minus 1 by 4 pi epsilon naught times q naught upon r. Cos 180 was negative. Is it alright? That negative I missed out writing here. Okay? And now minus 2 plus 1 is minus becomes plus, right? Plus. Now as we substitute the upper limit and lower limit, upper limit is, instead of r we put infinity, so 1 by infinity, minus 1 upon we put the lower limit r. 1 by infinity is 0, so we will have only minus 1 by r. So the work done in taking the test charge q naught from p to infinity will be given by minus of 1 by 4 pi epsilon naught q naught upon r. Okay? Now, this is a conservative force. Work is done against this conservative force. Okay? So the work done in bringing the body from P to infinity will be negative of the work done in taking it from infinity to P. Huh? Because for a closed path, the work done by a conservative force is 0. So work done by the conservative force in bringing from infinity to P will be negative of the work done in taking it from P to infinity. Are you following that? So in that case, the work done in taking the test charge from infinity to P will be equal to minus, and work done in taking the body from P to infinity, which is minus 1 by 4 pi upstairs. So W infinity to P, work done in taking from infinity to P will be negative of this work done. Negative of this work done. That is minus 1 by 4 pi epsilon naught into Q naught upon R. Minus minus becomes plus now. So that's 1 by 4 pi epsilon naught into Q naught upon R. Are you following that? Now electric potential at a point, we want to find electric potential at this point. So electric potential at any point is defined as work done per unit test charge in bringing the body from infinity to that point. So 1 by Q naught, okay, this is your 1 upon Q naught, and your work done is 1 by 4 pi epsilon naught into Q naught upon R, Q naught gone. So 1 by 4 pi epsilon naught into Q upon R. So this is the expression for the electric potential at that point. Okay, can you do it? Okay.